Hello friends, I hope you all are good. I continue Algebra's M.C.Q.S. First, which of the following is not a field? A, B, C and D, right? But right answer is C. We know that by theorem I is a maximal ideal if and only if R upon I is field, right? I is maximal ideal of R. Here 3Z, 2Z, 4Z, 5Z is a maximal ideal of Z. We should remember it, PZ is a maximal ideal of Z if P is a prime, right? Here 2, 3 and 5 are a prime number. So 2Z, 3Z, 5Z is a maximal and R upon I is a field. But our question is not a field. So Z upon 4Z is not a field because 4 is not a prime. Okay. Now next one is the number of element in a field fx upon x square plus 1 fx is equal to z 11x, right? A, B, C or D. Our right answer is 121. Why? Z11x upon x square plus 1. Here Z11x is a field and x square plus 1 is a irreducible over Z11x is a irreducible over field, right? So that number of element in fx upon x square plus 1 is equal to order of fx. That's mean order of Z11x, and order of Z11x is 11 and degree of px. Order of fx is equal to 11 and degree px, that's mean x square plus 1 and degree is a 2. So 11 square is equal to 121, right? Now next is A is equal to this and B is equal to this. Option A is A and B are a zero divisor. B is A and B not a zero divisor, non-zero divisor. So we should remember the definition of a zero divisor, right? If A not 0, B not 0, but A dot B is equal to 0, then A and B are called zero divisor. Once again, A not 0, B not 0, A dot B is equal to 0, then A and B is a zero divisor. Here A not 0, B also not 0, but product of a two matrix A dot B is a 0. So we can call it is a zero divisor, right? R is a commutative ring with unit element. M is a ideal of R. R upon I is a finite integral domain. Then, right? R is a commutative ring with unit element. M is ideal. R upon I is a finite integral domain. Here M I की जगह पे हम M ले लेते हैं. R upon M is a finite integral domain. Then M is a prime ideal, M is a maximal ideal, A and B and none, right? Our right answer is C, A and B both. How can we say that? Solution is here. R upon I is a finite integral domain. Here given is R upon M, right? R upon M is a finite integral domain. But from our theorem we know that R upon I is a finite integral domain. If R upon I is a finite integral domain, then R upon I is a field. If R upon I is a field, then by previous example, we saw that R upon I is a field, then I is a maximal ideal, I is a maximal ideal, then every maximal ideal is a prime ideal, then IM is a maximal ideal as well as M is a prime ideal, then our right answer is A and B both. Now next one is, if order of G is equal to 49, then G is a cyclic, B, C and D, right? But here order of G is equal to 49. 49, that means 7 in the 7 square. 7 is a prime number, and we know that a group of order P square is a abelian. So here G is abelian, right? Now next one is H and K are a subgroup of G, then A, B, C or D. But right answer is H and K both are a subgroup of G, then H intersection K is also a subgroup of G. It's a right answer because our option A is H union K a subgroup of G, तो may or may not be, because H and K both are a subgroup of G, then H union K may or may not be a subgroup of G. HK is a subgroup of G. HK is a subgroup of G if HK is equal to KH by theorem. So our right answer is H intersection K is a subgroup of G. Now next one is order of G is equal to 30, order of H is equal to 15. Then H is, where H is a subgroup of G, A, B, C and D. Right? Here 4 option given hai. Now we calculate order of G by H. Order of G by H is equal to, by formula, order of G upon order of H. Order of G is equal to 30, order of H is equal to 15 is equal to 2. And G by H exists, so H is a normal subgroup of G. It's a right answer. H and K are a subgroup of G. Order of H is equal to 10, order of K is equal to 5, order of G is equal to 50, order of H intersection K is equal to 1. Then since we know that the formula order by previous theorem, we also know that order of HK is equal to order of H into order of K divides by order of H intersection K. Right? Order of H is equal to 10, order of K is equal to 5 and order of H intersection is equal to 1. That's mean 50. But 50 is a nothing but order of G is equal to 15. That's mean order of HK is equal to order of G is equal to 50. So that's why, and we know that HK is a subset of G, either equal or a subset of G. So, but here both order of HK is equal to order of G. So HK is equal to G. Now next one. G is a abelian group. Order of G is equal to 162. G has a subgroup, say H. Then what we can say that H, order of H is equal to 18, order of H is equal to 15 or order of H is equal to 13.3. Then by Lagrange's theorem we know that मैंने अगले वीडियो में भी Lagrange's theorem करवाई है. इसके हिसाब से order of H divides order of G. 18 here 18 divides 162, 15 divides 162, 13.3 divides 162, but 18 divides 162, then SH is a subgroup of G. Now last is so our right answer is A. Last one is order of G is equal to 25 and number of normalizer of A in G is a 5. Then find out the conjugate class of A. So for this we should remember this formula. Order of class A is equal to order of G upon order of NA. Here order of G is equal to 25, order of NA is equal to 5. So our right answer is 5. Thank you.